a lot of cool applications with it, and and multiple avenues to to fitting ERGMs on using egocentric data. And then we're going to finish up talking about bipartite networks. The really neat thing is that with ERGMs, you have this ability to simulate. Once you have a set of egocentric data, you can use kind of the aggregated information from your egocentric data to simulate larger networks based on the properties that you see. And this really offers what I think are two really important opportunities to researchers who, even if you're interested in what's going on in a broader population, you don't have the means to because of the difficulty of collecting data. The first thing is that by simulating larger population-sized networks from egocentric data, you're able to assess the range of possible network-level structural properties from networks that you couldn't get just by asking what's going on, right? So if you're interested in, okay, given, in a certain population, how many isolated components are there in the network, or what's the connectivity like? You can't really get that if you're asking individuals who they're tied to and, and whether those people are tied to each other. But if you can use those data to kind of estimate a range of networks, then you can look at those simulated networks and say, okay, like these broader structures, these are the sets of broader structures that are possible. The other thing that's really useful for this is that because you're able to simulate pseudo populations of full networks, right? This gives you the opportunity to create populations in which to create simulations for things like disease transmission, right? You're going to learn more about the EpiModel package tomorrow. The EpiModel package streamlines this and really capitalizes on this feature. And in many ways, for setting up, it streamlines the process that hopefully, some of the things I'm going to show you are a bit redundant, right? And EpiModel, in some cases, will just kind of let you do what you do. I also think that this ability to create simulated networks from just aggregated information from egocentric data, I think it's pretty conducive to collaboration, right? Suppose you're interested in a population, you want to simulate, say, disease transmission, and you have theories you want to test, but you can't go out and collect your own data. And the issue is that the data that are available are restricted, right? So you can't get access to individual respondents' information, right? If you reach out, in theory, you could reach out to a group that does have those data, and they could provide you the aggregated information about trends, from their sample, and give you those, and you could use those to construct the networks that you need for your simulations without the need to ever access any of that identifiable information. So again, following this, right, I'm a recent hire of the Connect Lab up at Northwestern. Right, they do a lot of collecting egocentric samples of MSM in Chicago and using those to create population-level networks for simulations. And a lot of how they go about doing this is once they've collected the data, they create aggregated, descriptive, in ERGM terminology we call them target statistics, and feed them into an ERGM model to then generate the network. When you're doing this approach, this is assuming that you've already collected your data and you've already done the analyses yourselves to get those aggregated target statistics. One important thing to bear in mind is that when you're fitting this, you're going to want to know the density of your network, and you're also going to want to know the desired number of edges within the network, because your sample of respondents for your egocentric network is going to be much smaller than the population you want to simulate typically, right? And then as you're scaling up the size of the population that you want to simulate, you need to take density into account and the desired number of edges just to make sure that things are going okay. The EpiModel package does a lot of this for you in with very simple arguments. Again, if simulation of disease transmission is your end game, EpiModel will offer a path forward. But just to kind of outline how the basic process goes, right? It starts. You want to start by creating an empty network object from an n by n 8 matrix, and your rows and columns are the number of nodes that you want in your simulated population. If you are interested in effects based on vertex attributes, you will need to, once you've set up this matrix, manually add based on some distribution those attributes. And again, that's sort of at your discretion. And then, like I said, because of scaling, you're going to want to specify the number of edges that are on the network based on the density that you've derived from your egocentric sample. And then, again, because the example here is MSM and concurrent ties is very, very important in that context, right? You may also want to calculate some of those kind of basic structural aspects as well, right? In this case, right, the target statistics that I was given is that approximately 12% of ties are concurrent, or among nodes with concurrent ties, and then you calculate that. And then what you do is when you're using the ERGM package to fit an ERGM, right? The key thing is like you're specifying your terms, you're specifying your model, but again, that network object that you're feeding it is empty, right? It's going to be simulating the edges. The key thing is then you're going to be feeding in the aggregated target statistics that you've calculated beforehand, right? And the key thing to remember is that for each term you add, right, you want to make sure that you have the target statistic specified within that order. And again, this is just basic, density term, concurrent ties. The output and the interpretation is more or less the same. You can run diagnostics. Again, when you're kind of starting with an empty network and simulating, the diagnostics aren't always, the most useful or applicable. But again, like once you simulate, once you fit an ERGM using egocentric data, you still have access to all the same sort of MC-MC diagnostics and goodness of fit, visualizations and such. Another thing, again, going back to this point that you want to include target statistics for each term that you include, right? Like for instance, if we wanted to expand the model to include racial homophily, right? So the node match term on race, given the set of target statistics that I was provided in this very simple example, right? There is this in the aggregate racial homophily, proportion of racially homophilous ties, right? But also then there are breakdowns by racial categorization in these data, right? If you're not interested in within group variation, right, you go with this sort of aggregated measure, but and I'll come back to that. But if you are interested in within group differences on the sort of term, when you set diff equals true, and this is the same way you specified it in ERGMs in general, right? You're going to need to feed it in individual target statistics for each of the categories within that variable. And then coming back here, right? I should say I'm going to be posting some example code that should function as a template. These models, this code is built on the fly more for building your intuition on how to program these things. With the data and these targets, there are a lot of degeneracy problems like these. Anything I'm providing here is not the basis for an actual substantive study. But once you fit that model, right? Again, same interpretation of the results. But then you have the simulate function, right? And this is kind of, if your end game is just creating simulated networks for use in at a later stage in your project, right? This is kind of the end game, right? And here, just based on this simple model, I simulated one network. And again, here's a population of I think it's 1,000 nodes. Again, with this racial homophily term, and this is what the network would look like. And you would generate a set of these and then run simulations on each and derive your findings that way. Okay, so that's a process involving a lot of steps, and it's not too difficult, but it can be tedious. What if you don't want to generate the target statistics on your own? This is provided that you do have your own set of egocentric data, right? What if you don't want to do that? What if you'd rather have it, kind of streamlined? The other thing is, what if you have survey weights in your data collection, right? And then how do you incorporate that? A recent addition sort of in the environment of ERGM tools in R is this package called ERGM Ego. And it's really great. It's really neat. It allows you to feed in directly your full data set of ego networks. And it'll automatically, and then once you've created that object, if you're looking for those target statistics, you can ask it for it and it'll give them to you. Again, if you have survey weights, if you're familiar with the survey R package for incorporating survey design into your analyses, it's built off the same syntax and arguments of that. kind of functions as a wrapper for that. So pretty easy implementation of survey weights in a way that if you were doing it yourself might just get a little tedious. And another thing, like I said, one of the big obstacles or things you need to keep in mind as you're simulating networks from egocentric data is you need to think about scaling once you're attempting to simulate a population larger than your sample. There's pretty easy arguments within the ERGM ego package to do so. And so as an example, I'm using data. I've used data from the 2004 GSS Ego Networks module. We've had plenty of discussion about those data already in the past few days and its different methodological challenges. But again, what makes this a good kind of example for learning this is that it does have survey weights that can be incorporated. So probably the most difficult thing to get accustomed to when using the ERGM ego package is the data set that you feed it in comes in this format of an EGOR object, right? It's the EGOR package. And an EGOR object is effectively like a list containing 3 separate data frames. The first one is going to be information about your alters, right? So the people that your respondent has nominated. Your second data frame that you're feeding into this list is your egos, your respondents, and their properties. And then you have the edge list of nominations by respondents of their ties. And then once you feed those data frames in, you have to specify which variables are your respondent, ego's ID, their alters ID. Within the edge list, then, what's the source of the edge and what is the target of the edge? And then here this is ego design. If you're familiar with the SurveyR package, it's just a list containing the same arguments that you would use in the SurveyR package. The one caveat I will make is a final thing before I revisit this is the last thing you want is there's this argument for alter design, right? So these data suffer the problem that Carter was warning us about earlier about Matt creating a cap on the number of nominations, right? One of the things that the EGOR package does really well is you can specify in the construction of it so that in analyses it takes into account what is. I think the main feature of this alter design argument is just specifying was there a ceiling on the number of ties. But from the get-go, when preparing your data for using the ERGM ego package, right, you're already taking that into account. One caveat I will make, and I will say that as far as referring back to this presentation and trying to use this package on your own, this package in its current state, I'm in a bit of a discussion on GitHub about addressing it, is it can be a little finicky with naming conventions. These are the conventions for naming your key source target ego ID variables in most of their documentation. I would suggest if you can rename those variables of interest just to be consistent with this format. It plays most nicely this way, and it saves everybody a lot of trouble. Just real quickly, kind of going into each of these objects. So here we're looking at alters. Again, this is your alter level information. So your first column is going to be the ID number. ID numbers are organized within participants, within respondents, and then what their ties are. So we see here that for ego 3, right, we have 1, 2, 3, 4. Then for ego 5, it refers back to 1, 2, 3, et cetera. But you're going to want your alter ID, and then you're going to want to index it by who nominated that particular alter, and then you have their information at the node level. And then again, same kind of node level information for egos, and then the edge list, which is pretty standard edge list. But you do need to index that this is the edge list within a particular ego and who they're nominating. And then once you do that, right, then you're fitting the model pretty much. This is descriptive statistics, right? So this is breaking down degree within the GSS data. From there, right, this is a breakdown of degree by sex. roughly what this is telling you, it is a lot to look at, but it is saying that women are nominating more alters in these data than men do. Rather than trying to inspect those, you also do have descriptive visualizations, which you can break down by nodal attributes. So again, we're seeing men typically report. There's a higher proportion of men reporting fewer ties, and then women are have a higher proportion of reporting higher numbers of nominations. Mixing matrices, as Jim said, right, often very good for building intuition about your data. Those functions are built in as well. And then as far as fitting your model, right, you're going to be using the ERGM ego function, but it's pretty much how you would fit an ERGM in general, right? And again, how you would interpret it as well. Then then the next step is, if you are trying to fit an ERGM or a simulated ERGM on a larger population size, right? This is where it gets convenient. You have the control ERGM ego function within this argument, and you can specify your desired pseudo-population size. And you'll notice, if we compare back to the last slide, some of the coefficients change because it's adjusting for that different scale. And as you would with ERGMs, similar diagnostics, we're seeing here that, with the degree term, the model that we specify here does not fit very well. But again, this is just sort of for illustration and intuition building with how to set these things up. And then this is just an example of an expanded model. I've included a degree for isolates since there are more isolates than we would expect at random, and then various homophily terms. Yeah, and again, slightly better model fit, but definitely messy. Again, we're seeing the degree 5. The degree 5 here is way off, and that's an artifact of that ceiling of when people were nominating a lot of folks, right? They were capped at 5. So any questions on fitting ERGMs from egocentric data? Yeah.
Actually, goes back to eCourse. So I've tried to use it before, but let's just say hypothetically, someone collects data and they don't add alter ties.
Okay. Yeah.
When I tried to put it into eCore, it was like, no, can do either your alter ties or else that's it. It has to fit.
Yeah.
It have to be in your data set. Is that just like you have to?
My only experience with this is working with data where there is that. I'm not sure. Does anyone know? I would assume that maybe there was a specification for just treating it as directed nominations, but I've only ever worked with data that have that functionality or have that feature. Anything else before moving on to bipartite networks? Yeah.
What if you don't know the size of the population? So you saw that you could put in the population. So if you don't know what that is,
I would say at that point, just if you're interested in sort of what if, for example, disease flows or diffusion or something like that. If you have a sense of the range, just simulating across that range. Jim.
I just think you guys can go over it quickly. On the mixing matrix, or decimals?
Oh, so the decimals there, that's occurring because that was the mixing matrix on the. It's a mixing matrix on. I think it has to do with the survey weights. I think it has to do with the survey weights. Yeah. So, like for instance, yeah.
You don't know the real value.
Yeah.
This is an expectation. I can offer two weird tricks if you're doing this. They save you some pay. Really simple things. You showed it really clearly. But one thing that's not, I don't think it involves, when you create your base network, you can do it exactly like you said, and that may work. But when you start with an empty graph, when you do your simulation, right, you're forcing the ERGM to have to start from nothing and add a bunch of ties. And in a really large network, that may cause problems if you don't burn into them. One thing you can do instead of seeding it with an empty graph, just use the SNA package, the R graph routine that produces a random graph. Produce just a random graph or a training graph with the expected degree equal to your population. And it doesn't matter if it's dead on. That doesn't, you're just going to give it a starting point that's more in the neighborhood of where the real data is. And that will speed up your convergence rather than starting with an empty graph. Because it's closer to what the real network looks like, and that graph has no ties in it. And it's super fast, it's one step, and it will sometimes make a big difference when you actually go and run stuff. The other thing is, if you're getting weird results and stuff and things aren't working well, you may need to adjust the MCMC iterations and increase the MCMC interval to control, because most of our defaults are calibrated for relatively small networks. I've definitely encountered things where there are models that they weren't working with a large network, and all you do is tune up the MCMC, and all of a sudden everything works. And the problem was just it wasn't mixing well enough. And so those are two really simple tricks, but when you're dealing with these really large cases, you may run into things where you need to adjust those settings. And so that will save you a lot of grief if you just keep those two things in mind.
Yeah, thanks for that. The random graph suggestion, I hadn't seen that. That makes perfect sense.
For some reason, everyone's like, let's initiate with 0, but you can definitely have things where your stuff doesn't work and you're pulling your hair out trying to figure out, I don't understand why it doesn't work. And then it turns out that the issue is just that it was just taking a long time to burn in because you started so far away from the target. And you can increase your burn in and it will eventually work. It's just, why do you waste your life waiting for this thing to emerge when you could just start it out in a more sensible place?
Which is another thing. I'm gonna have the R script with examples of this code up shortly. But I do find with some ERGM tutorials, right, like when you have the R script to follow along, because things take forever to run, you often end up staring at your screen waiting for the thing to finish, and it messes up the flow of the whole tutorial. Anything else before bipartite networks? Bipartite networks I'm going to cover just fairly quickly because I do think as far as setting them up and working with them, it's not too far off from just working with ERGMs generally. So when we're dealing with two-mode networks, right? In a lot of times with the questions that we have, just taking the two-mode network, multiplying the adjacency matrix by its transpose and getting the one-mode projection, a lot of times that's sufficient. And when you do that, you can work with the standard ERGM, not really have to worry about that two-mode aspect. If you are kind of staying true to that matrix multiplication, you are going to have weighted edges, and then some of the things that Jim was talking about earlier, you're going to have to implement, which again can be tricky. Might be finicky. Maybe you don't want to do that, right? Maybe that's maybe you'd like to avoid working with weighted ties, and that would be one motivation for avoiding working with the one-mode projection. Alternatively, right, depending on your question and your interest, right, you might think that there is something about properties of nodes in each mode that matter for the structure of the network that you're interested in. Like, so for instance, like if we were thinking about like graduate students and where they would want to go, right? In a one mode projection, you might be able to have a node level property for the students of like, okay, well, what is their discipline? What are their interests, right? And then you could just do like homophily term. But let's say there's something about universities that graduate students apply to and attend, right? Like say you're a social psychologist and you really want like an interdisciplinary lab space, right? Not every university has that kind of lab space for that. And so those schools that do become a big draw for students with those interests, right? That would be a property of the school level node, right? That might lead to tie formation in a way that if you just had the single mode projection of students and their interests, you wouldn't be able to capture. Another thing is that you could, in theory, have two networks with different configurations of the second mode nodes. But when you do that transpose, when you get that single mode projection, those single mode networks would look identical with the same weights, right? So you in some cases, it's a mistake to overlook the properties of or the structure of one mode in the network by focusing just on the other one. Fortunately, ERGM offers support for bipartite networks, and this is in the form of it has just by default mode-specific terms. When you create a network object, it does have that specification, like is this a bipartite network or not? And so when you feed that network object into ERGM, you're easily able to specify, to include terms based on which mode you're interested in. Most mode-specific terms are pretty similar, if not identical, to their normal counterparts, or single mode counterparts when you're specifying ERGMs. The only difference is that there's usually a prefix in the term that you're including. So the prefix B1 would be saying, match or take into account the properties of nodes specifically in mode 1, and the B2 prefix is for your second mode. And examples of this is, again, if you're interested in node match, right, matching on categorical variables, something like racial or gender homophily, you would just include that B1 prefix there. And similarly, again, if you're interested in the continuous covariate, right, you would have that B2 prefix. I think the only thing that is worth kind of elaborating on a bit more, as Jim talked about earlier, with ERGMs, you have the ability to include terms for K-stars, right? These kind of distinct shapes that can occur within networks, and you're interested in their occurrence compared to in networks compared to chance, right? When you're doing regular ERGMs, it's thinking only in one mode. When you're including terms for K-stars in a two-mode network, you do need to kind of bear in mind that stars occur in two-mode networks, but what's usually happening is that it's two nodes in one mode being connected through a node in the second mode. And so you need to keep in mind which kind of star, right? Basically, what is the focal node in those star configurations? So if you're interested in two nodes in mode 2 being connected by a node in mode 1, you're going to include a K-star term with the B1 prefix. But if you're interested in two mode 1 nodes being connected through a second mode, or the second mode's node, it's going to be B2 star. And then within the term as you specify in the model, you include an integer or a range of integers if you're interested in a variety of different forms, right? Specifying 1, 2, 3. Here I have 2 stars and 3 stars, but you could go up to however many stars in theory. There is one thing to keep in mind, right? When we some things like as simple as like node match, right? Those are typically treated as dyadic independent terms in a single mode network in ERGM, right? Because node match, right? B1 node match is basically saying that it's implying, right, this 2-star here, right? It's that these two people share a tie through this based on some property that they each have, right? The inclusion of that kind of intermediary node makes it lose that dyadic independence, right? And so it leads to a bit more difficulty in fitting, especially if you're working with larger networks. So that's something to bear in mind. And then just as a quick example of including these terms, putting these terms into use, right? I'm using data here on course enrollment among college students at Notre Dame. And here I've in the code that I'll send along, there's the code to build, clean that data set. But basically, I just fit a very simple ERGM here, where it's the network, the two-mode network of students being linked through the courses that they enrolled in. Simple density term. I created a node match term for courses by department. We would imagine that students who are in the same major, right, take courses in the same department. And so we would expect that courses are more likely to be linked through students if they're in the same department. And then I included a couple K-star terms here, 2 stars and 3 stars, of courses being connected through students. And again, what we see here is that courses in the same department are more likely to share students. We see a greater number of 2 stars in this network than we would expect by chance, but we see less 3 stars. Again, as with ERGM ego and just ERGMs in general, you have the same sort of MCMC diagnostics and goodness of fit tests. As you can see, this model was not fit very well at all. But one thing to bear in mind, that when you do plot your goodness of fit, you actually do, when you're looking at your degree term, you have separate plots for your degree of modes in one node and modes in the second node. That's all I have for bipartite networks, because I do think the implementation of it, once you get the hang of ERGMs, is pretty straightforward. But if anyone has any questions, we can leave it at that. Yeah.
Just have more of a logistical question. So I did bipartite networks from implementation, had big issues with convergence.
Yeah.
So I had to really, more so just did a dyad independent model. I couldn't really look at the structural features. But they just take a really long time to run. So maybe this is just more of a logistical question about just running ERGMs in general. I mean, my computer would be like smoking by the end, but like it will take hours or days, and I'm still learning about R, so it could be something that I'm doing on my end, but are there just ways to, like, do people just run ERGMs on a separate computer and leave it, or like how, I'm just curious about the logistics of this.
Well, I think it depends, right? So it does depend on how large your system is and what you're doing. Some models are just really expensive, and yeah, sometimes we use servers for things, but in my experience, if the network isn't super huge and there's not some very good reason, if your models are taking a really long time to run, or a really long time to converge, it's often a sign that your model's not cutting nature at the joints. It's like, have you ever seen like great show like Mark Yan? This is a while back, but he still anyway, the famous chef. And if you watch cooking shows, you see people taking Mark Yan takes a chicken apart. And when he does this, he picks up his chicken and he has a cleaver and he just kind of like touches the chicken, and the chicken just falls apart. Or if you read the Chuang-Chi, you know the tale of Dexter's Butcher, right? You cut nature at the joints and it just falls apart effortlessly. And ultimately, right, if I try to cut a chicken, it's not pretty, right? I mean, it's like some crime scene, and it takes me a long time. And I think ERGMs are a lot like that. If you pick the right terms and that really capture the dependence of the network, the model fits almost magically fast, at least often, and it just sort of works. And then when you're trying to like force it to fit, and it really doesn't want to do it, the model is, I call it strained. And anyway, that's a long term I think about it that way, but it's a good metaphor for what's going on. You've given the model these levers to pull, and it's trying desperately to explain your network, and it's in the situation where it pushes this lever too far, now this feature is wrong, and it pulls this other lever back to fix that. But now the model is off again, so it's desperately working these levers, trying to make this thing go. And if it's spending hours trying to do that, that's often a sign that the levers that you're picking aren't the right levers. And it can be frustrating because often they seem to like they should be the right levers. But it usually means they're not. And so it's often a sign that rather than putting more computational effort into it, you may need to back off and rethink. And that can be challenging, right? Sometimes we don't know how to, and sometimes there may be things that you can't do. Because for instance, it might turn out that the reason your network is clustered is because of an exogenous variable that you didn't measure. And no amount of dependence terms that you have access to is going to properly recover that heterogeneity. And so you're not going to do a perfect job because the thing you need to explain the network you just don't have. But so sometimes there are limits and you may have to compromise in some way. But otherwise, I think going back and rethinking the model framework is reasonable. Cutting back your dependence terms down to a minimal specification. And then don't be afraid to try things like, for instance, using MPLA to fit. Often, if it's very strained model, MPLA will probably not be great. But what you can do is simulate, going back to what you're showing, simulate from that model and look at where it's screwing up. So here you have an example where it's screwing up, right? That's actually educational. Learn from the failures. I think we don't spend enough time. This is a general modeling thing. This goes back to things that we learned the hard way back in the day with agent-based models. So like the models that didn't work were the most interesting. Unfortunately, I don't make it into the paper. But it's all the explanations where I have a theory about how this works, and I implement it, and I spend hours implementing it, and then I run it, and it doesn't do what I expect. And I'm like, why don't you work? But that's telling me something. I was wrong, right? And that means I've learned something. The whole goal of science is to be wrong, right? We forget that, right? It's all the theories that didn't work that tell us about the world. So when the model you think should cut nature of the joints is not working, going back and figuring out, if I simulate from some crude estimate of it, what is it getting wrong, may give you a clue about what needs to So that's what I would sort of suggest. But as a general matter, with, with ERGMs, if you're finding that like you just can't make the thing work and it's struggling and it's running forever, it's, in my experience, usually a sign that that specification has too much dependence in it, and probably it's because somehow you're not cutting nature at the joints, even if you think you are. And I do think then standing back and trying to rethink how might it work. Is there another way to approach this? Usually that works better, and it's one of those things where when you find the right specification, and all of a sudden the thing that was taking hours to run, it's like it clicks and it runs. You're suddenly like, oh, okay, that was the right answer. But until you see it, it's hard to see.
I would.
Just a couple other things. If your model is all dyadic independence terms, all Wolff terms, that is taking all this time, there's something wrong.
Yes,
Stop
it
this.
was. It was no match. Or B1 no match.
It's
Yeah.
all node match terms, nothing
Yeah.
else in it.
But it's B1 of it, which is the difference.
I see that.
Yeah.
I will also add, right, just as Carter was saying with, really rethinking your theory, also, and, this is best practice, just knowing your data. I mean, part of the reason that this is fitting terribly is I was choosing data for the purposes of Illustrated. I wanted a two-mode network where you would have nodal properties for each mode, right? And courses and students, right, have those properties, right? Like one of the reasons that the degree term isn't fitting very well is that as far as the number of courses that students enrolled, and this is within the time span of a year, right? We have this bimodal distribution where some students are taking 5 to 8 courses a year, and then there's this higher section where it's like 12 to 15. Some students in this data set within the year are enrolled in as many as 20 courses. I don't know how that works, if it's like half semester, something or another. I don't go to Notre Dame. I don't know, but this is one of the things, right? Like again, in this substantive setting of courses, yeah, lab, yeah. But again, yeah, but this is one of those things that like just as related to theory, also like you do need to know the substantive setting of your data. I think one of the reasons that so many of these examples are messy is I really wanted to communicate like how you work with data that have certain properties. But you do need to be very fluent with your data, which again, if you're conducting your research, you get there. I just, that didn't happen to be my position, right?
Well, I think that's a very important point. I mean, I think that's where your story is like really paying attention to your data and how was it produced and where did it come from. I think the network field has sometimes been, sometimes we haven't been so good about that. People like let me grab a data set from some website. I don't know where it came from. I don't know what it means, but I'm going to stick it in my thing. And people like me are the ones who create this problem, honestly. Because, when we're doing method development or whatever, people will pick something up and run it as a demo. But, of course, when you're really out there trying to make the model work, you really have to care about what's going on. There's so many things that will pop up, these weird features, really have to do with artifacts of exactly how is that data generated, exactly how it's produced, and when you analyze it, you do want to take that into account. So I think that's a really important point. You see strange stuff going on in the data, you check, why is that there? and how do I capture that? And it may be an artifact, or it may represent some special property of that process. But yeah, if you don't tell the model, that poor model is like, man, I got to figure out how to fit this degree distribution with these lumps in it, and all I have to work with are these levers, right? That poor model, that poor thing, how do you expect it to solve your problem? Right? So, be nice to your model. Tell it the things it needs to know to solve the problem.
To echo that point though, right, one of the arguments for fitting a bipartite ERGM like this rather than working on a one-mode network is, as I said before, you could in theory have 2 one-mode projections with the same weights, right? But they're produced by different things, right? That's that same issue of not fully taking into account the data generating process, right? You're seeing the end result of that one-mode projection, but you are for that moment ignoring the structure of that other mode that produces those equal possibility or equal outcomes. Yes.
I do have a question about size, because you both have mentioned if your network's not too large, and I have a sense that with bipartite that matters. Like, what do you mean by not too large? Or is there an ideal size? For example, I had 1,200, and I felt like that was maybe part of the issue I was running into. But if you could just, there may not be an ideal size of network for bipartite, but it seems to be particularly sensitive to.
1200 is pretty big.
Yeah.
So it's not that it's bad, it's that there's nothing wrong with having 1200. In fact, sometimes it's great, but in terms of like how long something would take, that's why I had my caveat. Because if your thing is running for a long time and your network has got 50,000 nodes in it, well, yeah, it's going to run a long time. If it was, 20 nodes and it's running for hours, right, then that's really saying something. So yeah, you may be in some cases just running into, it's possible if your system is fairly big, that's just a very costly thing. But one other thing you might try, this is another suggestion, given that you're running into that, you might think about, this is also an ERGM 4.0 thing. So this is now we're talking about this camera is not too much. I'm going to tell you something. I'm going to tell you something I shouldn't tell you. The default estimation mode in ERGM, which we use this Geyer Thompson Hummel scheme, which is very brilliant, but it can be finicky, and it's been tuned in a way. If you're an old-time ERGM user, which you're probably not, but you were ERGM before 4, there are a lot of models that fit relatively fast, and then you run ERGM 4, and suddenly they grind and grind and grind, and that has to do with the tolerances that have been set, and they've been moved in a way to try to make certain things more perfect and beautiful, and then run as long as necessary to get you to that perfection, which maybe you don't need. And anyway, some different design decisions were made, and obviously I don't completely agree with some of the design decisions. And so sometimes the problem is not even your model, the problem is that the tolerances that have been set are unrealistic. One way to get around that is to use an alternate fitting method. MPLE, although they're clever black magic things you can do with MPLE, usually, unless you know what you're doing, you shouldn't use that as your definitive method. But if you use the stochastic approximation method that is supported in ERGM, that nowadays I would say is often a faster and, in my opinion, often more stable way to do things. And so I myself often nowadays use stochastic approximation instead of Geyer Thompson Hummel, which, being on the StatNet team, I shouldn't say that, because that's the PNet people's way of doing it. I love my PNet colleagues. They always use that method. We have always used this other method. They both work. There's nothing wrong with either one of them. They're different trade-offs computationally and they're arcane things, but they all lead you to the same place. So it's not a second-class approach, but you may find that it is much faster for your problem to use stochastic approximation. So that is one thing if you're running stuff and it's getting bogged down, you don't know why. Try doing the stochastic approximation and see how it works. You may find it works much faster and with no issues. And if so, nothing wrong with it. It's a perfectly fine thing. It's just a different computational way of getting to the solution that may get there faster in some cases. Not always, but right now, I often find that to be helpful in some of the networks I work with. So that's another thing you might try, especially if it's big.
Anything else?
Thank you, Tom.
Cool.